look like. So if I go like this, then the distance from that point 2, 0 to the function at the floating point, and that floating point is going to be x, and then whatever the function value is, that'll be on the function. It's found by minimizing the distance formula expression. So there's the distance formula where you just subtract the values and square each one. It's just Pythagoras. Whoops, I didn't type in. That should have a little square there. If I type it in now, that'll mess it up. I'll make sure that's there for your answer key. Note, there's a clever little trick that if you're minimizing a distance, you can actually minimize the square of the distance, and you'll find the same x value if you think about it. The shortest possible distance is also going to be the shortest possible square of the distance. So you could eliminate the derivative. You could eliminate the derivative with a square root in it if you wanted, but we're using our calculator, so it doesn't really matter, does it? We can simply go to our calculator then and type that equation in that we're trying to optimize. And if I go to it here, and I'm now going to turn off my original function because it gets to be in the way, I think. And if I go down, here is that distance formula function, and I'm going to turn that on. And you'll see there's x minus my 2 and y minus my 0, and that's squared. I got it the squared part this time, and then it's all raised to the 0.5 power. That's the square root. Okay. Now the thing about this is we know from looking at that graph that the distance was on the neighborhood of 1 or 2 units. So when I go to do this graph, if I just hit the graph, I'm seeing it go down very low. And actually, I wouldn't need to change this really. Just knowing my calculator skills, I just need to find this minimum value. It looks like they're all going down to 0, and that's puzzling. But if you were to think about it, anytime that our original function gets somewhere close to the x-axis, the distance actually will be only like 5 or 6 units, whereas this is in hundreds of units away because the function is going quite high. So we just need to find what is this minimum value around this area. If I were to zoom in, I could do a zoom box and zoom in on that, but I think in the interest of saving time, I will not. I just need to know what is the minimum value of this function right in that region. So I do second and trace, and I want to find minimum value. So this is 3. And then I don't want to be doing the 0 function. I want to jump up to that one. And as long as I get close to it, but I'm above it on the left, I'm good, the left bound. And then I just need to get past it here. And I'm definitely past it there. And then I'm going to pinch off. And okay, my minimum value there is when x is 1.297. 1.297. And there is my minimum distance, less than 1. Okay, so if it's asking what is the minimum distance, it's 703. If it's asking when is the x value going to do that, it's 1.297. What is it asking? The point that's closest, the point is going to be when x equals. I'll type that in on the final one because the way I'm revealing these, but that is the answer. I'll type that in later. And so here's the next one. The rate at which the function is increasing or decreasing if the x value is increasing at a rate of 3 units per minute at the moment when x equals 5. Okay, so this is related rates. You need to find an equation that relates these two things. It's simply our function value. And so I just take the derivative, do it very carefully. You get that implicit kind of a differentiation where you bring the 4, multiply it times the 2. Then you can't mess with the x because that's on the x side, on the inside, and then times the derivative of x is x prime. I'm just saving space rather than writing dx over dt. But I very carefully taken the derivative, and every time I bring that power rule number out in front, I don't mess with the inside, but then I have to tack on the x prime. Watch at the very end there, the derivative of 4x is just 4x prime because that x becomes a 1. Then the snapshot instant when x is 5, I plug in 5, dx dt is my x prime. That's just 3 units. So I very carefully plug in the 5s and the 3s, and I crunch those numbers, and I get, and that's also units per, that would be units per minute. Okay, getting to the home stretch here. Determine the number of iterations that Newton's method must be performed in order to solve f of x equals 100 to 8 decimal places of accuracy, using 10 as an initial. Whoops, that is a 0 answer, but I can still show you how to do that. So if you have this function equal to 100, then you would simply subtract 100 from both sides. All right, so I would have a new function then that will be the original function minus 100 equals 0. So if I go to the calculator and then I go to y equals, and I'm going to go way down here I'll go to 6, and I'm going to type in vars over to y vars, and then I'm going to choose option number 1, and then I'm just going to do minus 100. Okay, that's my new function that I just want to find the 0 of, so that will work. So then I know that that's y6, and then I will change this function up here to be, my derivative will be y6 vars, and then 6. So now I'm taking the derivative of y6, and then I do second quit, get that clean screen, and I then do 10 as my initial guess, and I hit enter, and now that's my answer. So then I do second answer, then minus, and then I want to do y6, so I do vars over to y vars, choose the function, I choose 6, I want to type in answer, second answer. You've all done this hopefully. Then I divide by the derivative of that, which is still y4 for me, so I do vars, and I go over function 4, and then I do the same thing, parentheses, second answer. I'm nearly done, and now I've got my little template set up, and I should get something around like 8 or 9. Okay, 7, so that's 1. Let's count. I would write that down. Then 2 and 3 and 4, 5, 6, 7, 8. I'm looking for these last ones not to change. 8866. 8866. Okay, 9. There we go. It took 9 times to get that not to change. All right. And I'm going to take a screenshot of that for the answer key. And then if I go back to the answer key, that would be what I'd write in. I had found an original 0, so I've got to correct this answer key, but that'll be corrected in your version. And then find a value that satisfies the mean value theorem over the closed interval. Okay, so the average rate of change over that closed interval using the endpoints is, and going back to these values up here, it's going from 0 to 126. As it goes from -3 to +4, that's a change of 126 over 7. Okay, so that is actually exactly 18. That was a bit of a fluke. Then I need to find a C value such that f prime of C is 18. That's where I go back to my calculator. I go back to y equals. I find that an easy way to do that is to go down, and I'm going to turn off some of the other things here. I'm going to turn off this. I'm going to turn this back on, but I'm going to go back to my y1 equation because I need it here. Sorry about this. You can fast forward through some of this. And then that's my y1 equation. I turned that off already. Then I'm going to turn that equation off as well. But then I'm going to turn this equals 18 on. That's my graph for 18. So there's the line coming across. When does my derivative equal 18? There are going to be three values, 1, 2, and 3. I found all three of them here. And you can see that there's negative 2, 0.031, negative 0.0316, and positive 2.732. Okay? Then finally, a little L'Hopital's rule problem. I've set it up using the function. If you have 30 minus the function when x goes to 0, of course your constant term is the only thing that's left. So 30 minus 30 is 0. 1 minus e to the 0 is 1 minus 1. That's L'Hopital's rule. Indeterminate, 0 over 0. Make sure you say that. If that is indeed true, you want to verify it. So that limit then, when you take the derivative of the top, that 30 goes away. And, oh, that should be a minus. Oh, look at that. That's a minus 4. And then minus 4 over minus 1 is then, in fact, a positive 4. So that limit would be a positive 4. And that should get you to the end. Hopefully that was helpful. Thank you so much, everybody.